Okay. Yeah. Let's start our maybe kind of story in indoor SLAM systems. Yeah. We want to discuss today is length and structural constraints in indoor SLAM systems. Maybe those types of features can help us in improve the accuracy and efficiency and robustness of our systems. Okay, yeah, let's start. Yeah, we have three sections: background and motivation, and then features. And the final section is constraints and how to optimize those features in SLAM systems. Yeah, yeah, this is first section. In indoor environments, yeah, it's very special. Maybe, yeah, let's say, and since compared with outdoor environments, we will see some low or non-textured regions, and you can see those white walls and ceiling, floor. Something most of them are very low textured, and furthermore. And since those man-made scenarios have some special structure elements, so it's also very special and based on those structural elements, we can try to make the system more maybe robust than ever before, maybe. Yeah, first of all, let's revisit some traditional but popular systems. And here, I will focus on feature-based SLAM methods since, as you know, yeah, there are lots of methods, maybe making use of direct method or some semi-direct and feature together. So yeah, most of those methods like SVO, DSO are also very popular in the community. But here we will focus more on feature-based SLAM methods. It means we will maybe use a kind of method to extract some interesting stuffs from the scene. Yeah, not every pixel, but maybe in some edges, some special pixels. Then we can use a descriptor to yeah, to represent this let's say point. Then we can check this point in different views. Based on this strategy, we would like to call it as feature-based SLAM methods. Okay, maybe at the early stage, most of feature-based SLAM methods are based on point features like OpSLAM, PTAM, and so on. They have achieved a bigger success. But in indoor environments, since those point features are very difficult to achieve in low or non-texture regions. So to solve this problem, yeah, people, yeah, it's a very direct idea to extract more features, right? And besides points, people want to extract lines since it also rely on a single RGB image, RGB image only. So it's a same strategy for point. So it's a very direct idea.
Yeah, maybe I can ask if there's a way to use a different mic, or because we have a lot of background noise, metallic.
Okay, yeah, yeah, let me check. Yeah, let me check whether this one is better.
I see familiar faces today with us. Couple repeating. It's good to see the people are coming back and back to the events. Means that we're doing something right. Are you using Ubuntu? I just noticed. It's very brave. I sometimes tried using it, but every time something happened and it changed something with the drivers of my GPU.
Hi, Peter. Yeah, is it better now?
A bit better, yeah. A bit. Let's see. Let's start doing it, and we'll see if it's better. Now we don't hear. That might
Hi,
be.
Peter. Can you hear me?
It's a bit strong now. If we can make it dialed down a bit.
I cannot hear you.
You can't hear me. Oh. Yes, no?
Okay, yeah, I can hear you. Is it better?
A bit better, but it's a bit strong also.
Okay.
Yeah.
Let me check.
What is that? Wow.
Okay, but I am not sure how to make it.
Just move that left. Just move the input volume to the left. I think it'll help us. Yeah, this bar. Let's see now.
Yeah, it's better.
Oh, yeah, yeah.
Okay.
I think it's good. Yeah.
Okay. Yeah. Yeah. Okay. Cool. Yeah. Let's continue. Yeah. Yeah. Let's continue. So for those line features, yeah, if you only use it as if you only use a line as independent feature, it will be very an economy, since you need more time and to extract line features. But yeah, if you only use 2 points of it, it's very it's really not a good idea. So people began to check the relationship between those lines. If, for example, for parallel lines, maybe you can extract a vanishing point from them. So then you, in this way, you can maybe cluster those lines into different groups. So yeah, based on this, you can maybe add more constraints, yeah, in your SLAM system. Okay, so for SLAM system, how to remove drift is an open task, since since for camera post estimation, it's very it's really a very basic topic in reconstruction, scene understanding, and so on. So a little bit drift maybe yeah, maybe will bring some maybe big effect in other applications. So for SLAM systems, we always we always want to achieve a high accurate post estimation method. Yeah. Yep. In this section, we would like to introduce features we used in our papers. And yes, there are some low-level features like points, lines, and planes. Right, it's very common features in lots of SLAM systems. And then for parallel lines, as I mentioned before, you can maybe got vanishing points. And for parallel or perpendicular planes, you also can use maybe use a degree between planes to to as your constraint in your post estimation stage. And you can see in the right figures different maybe parallel planes are marked into the same color. And then you can see you also can maybe group those planes into different clusters. Yeah, and then you know yeah, for different clusters it means different constraints. So yeah, it also means different optimization methods, and maybe can bring accurate results to you. Yeah. Furthermore, if you have detected maybe perpendicular planes, perpendicular planes or lines, you also can make it to Manhattan world. The assumption of Manhattan world also is a very interesting idea, and we will introduce it in details later. And then for this IPR feature, it also is very interesting. And you can see the right figure. When if you detect two lines, and then yeah, instead of descripting those lines directly, you try to compute the cross point between those two lines, and here you try to describe this point. So it means instead of describing lines, we try to provide a descriptor for points. Yeah, it will be less computation. Yeah, it will be less computation, and it also can help you to match lines. Yeah, and yeah, for triangulation, you can directly obtain a 3D structure directly. So this is another, yeah, maybe it's not very new, but currently, yeah, some papers try to use this type of features. Yeah. And then, yeah, we have looked at too many deep learning papers. So deep learning and those networks have achieved a very impressive performance in computer vision tasks. So how to merge those learning methods into our system is also a very important topic, right? Yeah, similar to those low-level geometric features, this those networks also can maybe extract points, lines, and planes. But what's the difference? Compared with traditional, let's say, points extraction method like SIFT or ORB, these types of new networks can maybe achieve some maybe can extract more feature points, and also the distribution of those features are more even compared with a traditional method. Like for some not very textured regions, this super glue also can obtain some points, but for ORB, it's very difficult. In those right in those right figures, the first rule is the input RGB image. But yeah, here I show it in green, and then when you feed those RGB images, or even a single RGB image to network, and then you can achieve this plain instance segmentation result. It means the network can help you to find some planar regions. Yeah, we all know that it's very difficult to extract planar regions from a single RGB image, right? But network can do that. So how to use it and to extend our SLAM system, it's very important, right? Yep. Besides those low-level features, this type of depth normal maps estimation is also very useful. For example, And for this monocular SLAM systems, yeah, we know that it's very difficult to obtain a dense reconstruction. But if you can predict a depth map for each image, then it's easier, right? Yeah, the similar case can be found in stereo SLAM systems. Yeah, as shown in the right figure, we also when you feed the networks when we feed stereo images to network, we also can get the depth map of the target or source image. So compared with traditional maybe depth recovering methods, and this type of networks are very are also very accurate. So you don't need to worry about maybe whether the map is very rough or not. In fact, in lots of public data set, it's also very accurate depth prediction result. And then more high level information. We also can use the network to detect object, and yeah, yeah, a naive direction is maybe we can use this semantic information to generate a semantic map, right? Like fusion plus plus or some other methods, yeah. Yeah, based on this semantic map, yeah, you can based on this semantic map, maybe robots can interact with environments more smartly. Yeah, so it's also a very interesting direction. Yeah, this is dealing with reconstruction. In addition, people also can use these 2D bounding boxes or 3D bounding boxes to improve the performance of tracking process. So it also can be used in like maybe object tracking and also post estimation. So it's very open. We already have those geometric and length features. Yeah, let's say those features. In fact, maybe it's not very accurate to call depth map as a type of feature, but yeah, maybe let's say they are low level or high level features. How to use them in our SLAM systems? Yeah, maybe and here we will give some architectures and some ideas in details. You can see this is a monocular SLAM system. Yeah, from every single RGB view, we can extract LSD and all features. Yeah, as yeah, this part. However, you can see even this image is very textured, right? You can see different colors and yeah, and very yeah, very colorful, a very colorful image, but still only very very few features or very few pixels are used in this image, right? You can see those red lines and those green points. Yeah, yeah, there are only very few information, yeah, compared with the original image. So in our idea, maybe we can use the normal estimation branch to predict surface normal, and then yeah, it will be more dense compared with feature-based method, right? So in the top branch, you can see our surface normal result. But Yeah, it's more pixels we can be used in the system. But another important problems happens in happens currently. This is which parts could be trusted. So we all know for those for results from deep learning networks, we cannot use all of them, right? We need to find which part, which information can be used in the system. If we use all of them, maybe our useful features will be overwhelmed by the noise. So we have to, this is the most important in those joint systems. We need to find a method to remove noise and keep useful information, keep accurate information into our system. Yeah, here we propose a union sphere, and then we try to project those normals into the sphere. Then since they are normal vectors, so they will lay on the sphere, and then we make use of a mean shift method to find maybe try to cluster them. So in a mean shift manner, it means maybe at first we find a cluster and then we compute the mean of this cluster. I mean, this is a new mean, right? And then from the old mean to the new mean vector, this is a shift step. So this is why we call it.
Yan, I'm sorry, it's a bit hard to follow. What is that mean vector? What is that vector at the cluster, the mean vector, and how does it help us?
Okay, maybe we can regard it as 1 times 3 vector. Just 1 times 3, just maybe we just can write as 3 values. This is a vector.
What does the vector represent?
We can use it to present normals or normal. It means the direction of this pixel. For example, for the floor, a pixel in the a pixel on the floor, then the direction of the normal will be up forward. So this is there are 3 values to show maybe show the surface direction. This is a normal vector. And then when we project this normal vector to the surface sphere, we will as you can see here, we will obtain different groups. Based on this, we can remove those normal vectors that lie on other regions. So this is a kind of way to remove noise. This is what I want to say. How to select which parts can be trusted in your system, in your joint system. And the other parts of it are very simple. For the yellow one, you can use it to compute rotation, and then we use geometrical features to compute a translation. So this is a decouple manner, and then we will obtain some as usual, as those poles, 60 poles, and also the local map. This is a case can be used. This is a case that makes use of render features with geometric features. Here I would like to maybe make this mean shift process in details, you can see this is a predicted normal map. Yeah, you can see for the sofa and floor, since they are parallel, I mean the surface are parallel, so yeah, they are in the same color. Yeah, but you can see in some edges, in some edge regions, like this part, yeah, it's not very accurate, right? So based on this mean shift clustering process, we can remove those pixels, right? You can see we only you can see those red pixels for this wall, but this part it's it's empty. We didn't use information in this part. Yeah, this is the process of removing after layers from after layers that generated from networks. Yeah, this is the case. Yeah. Similar to that, maybe monocular system. For RGB-D system, it's a little bit easier, right? You have achieved depth maps, so it will be easier for reconstruction. Yeah, but in this part, since we can extract planes easier, then we would like, as you can see here, we also make use of normal vectors. But here we don't need to predict normal vectors based on networks. We can use our depth map to compute normal vectors directly. Yeah, it will be more accurate. And then we have 3D lines. We will use vanishing directions. We also feed those stuffs into this unit sphere, and we will have a clustering result. You can see different planes. Yeah, if they are parallel, we will mark them into the same color. You can see this is a surface of the sofa, and it's parallel with the handle surface, so they are in the same color. And even with a line, you can see if the normal vector of this plane is parallel with this 3D line, they are also in the same color. So this is the result of the clustering, and based on this perpendicular clusters, we can make use of Manhattan world. Yeah. This is the results of our paper, and you can see we can make use of those planes for reconstruction. But it's not very completed reconstruction. It's just reconstruct the planar regions. So here you can see some results. From points, lines, sparse planes, and also dense planar mesh. As I mentioned before, how to make use of the assumption of Manhattan world to compute 60 post estimation, right? Why it's interesting? Well, here, let's say, let's see this part. For Manhattan world, from my understanding, maybe the most important or most interesting part is drift-free rotation estimation. It means you can see this function. For traditional 60 post estimation, maybe we need to, we have different strategies, right? We have frame to frame strategy or map to frame. But for this kind of frame to frame strategy, it means current frames camera pulse is related on last frame. If you have some errors in your last frame, I mean, you have some errors you have some post errors in your last frame, then the error will be existed in current frame, right? This is a very important reason to lead to drift. Yeah. But for Manhattan world, you don't need to worry about that. Since for the first, let's since this is a kind of assume. So yeah, it has some limitations. But yeah, maybe we can check the inside first, and then talk about the limitations. First of all, if you for some general indoor scenarios like our office room, right? You can find some perpendicular walls. Yeah, for also maybe a wall is perpendicular to the floor or ceilings, right? And then based on this kind of perpendicular information, we will maybe we can build this Manhattan world. Like let's say this is a wall, this is a floor, and another wall. Then if you can find this type of thing, then you can call it Manhattan world. And just like the Manhattan Street in New York, right? Yes, most of buildings are very are standing in the same line, and they have some parallel and perpendicular relationships. So this is why we call it Manhattan world. And if we have this Manhattan world environment, then for the first frame, if you can compute the compute the rotation matrix between the first frame and Manhattan world, then you will obtain your maybe this rotation matrix. And for the case frame, the CK, you also can use this way to compute CKM, and then you can see if we use RCK plus 1M and RMW, and then you will obtain this RCKW directly. It means frames between the first frame and the case plus 1 frame will not affect the result of this frame's rotation estimation. So this is my idea of drift-free rotation estimation, right? You don't need to worry about intermediate frames between the k plus 1 frame and the first frame. So yeah, it means errors in those frames will not lead errors in this frame. That this is the drift-free idea.
Yan Yan, maybe just it was a bit hard to follow. Sorry for interrupting. I want to start from understanding the definition of Manhattan world based on Manhattan frame. So I think this was slide 16. We define Manhattan frame as a frame when we remove the outliers based on that spheric regions. And then we estimate the rotation, that part, it's a bit unclear, estimate RCM rotation from Manhattan world to camera. If you could again describe what this means.
Okay. In rotation, in post-estimation problems, we have 3 coordinates, image plane, and the camera coordinate, and also the world coordinate. And
the world coordinate?
Yeah, the world coordinate. Yeah.
The origin, you mean? The origin of the world's axis, or what is that? What does it mean, the world coordinate?
Yeah, traditionally we would like to maybe give the identity matrix to the first frame, then assume other frame, assume other frames we have to follow this coordinate. Then we call it as a world coordinate.
World coordinate. Okay.
Yeah, but it's not a real word. It's just yeah, the coordinate of the first frame. Yeah,
yeah.
It was
Representative sample. That's okay. And then we estimate the rotation from Manhattan world. What is Manhattan world in this case then?
Yeah, different with traditional 3 coordinates. For Manhattan world-based methods, we have another, we add another new coordinate named Manhattan world. Yeah, this is this M. Yeah.
How is it defined?
Sorry?
How is that coordinate defined?
Okay, yeah. We will also use use the first Manhattan frame. How to find this first Manhattan frame? Yeah, maybe for example, like this. This is the first frame of this sequence, and then we find some parallel and we find some perpendicular planes. Yeah, like currently they have orthogonal plane systems, and then we when we reproject those 3 planes or 3 groups into this mean shift, not mean shift, project those 3 groups into this unit sphere, we will obtain orthogonal axes, right? Yeah, since they are orthogonal. Yeah, we have x, y, and z in this sphere. Yeah, and then this coordinate will be called as Manhattan coordinate.
So you take that first frame, you take the normals of all the planes on that frame, you put them on a sphere representation, and that sphere representation of that first frame, instead of going as regular X, Y, Z representation, you're going a spherical representation, and this is your Manhattan world reference, right?
Yes. Yeah.
Okay.
Yes. Yeah. And yeah.
And when we say rotation RCM from Manhattan world to camera, what does that mean then?
Okay, yeah. For when we obtain the first frame's Manhattan frame, right? We call it as a Manhattan coordinate, Manhattan world. But this Manhattan world coordinate is different different to the world coordinate. They have some they have a kind of 3D rotation. Since for Manhattan frame, for this sphere, we only we cannot represent translation vector in this sphere. We can only check
rotation.
The rotation. Yeah. So here we only have this is the first question. We only have rotation, and then if we have the Manhattan world and the world coordinate, we need to compute. We need to align them. So how to align them? How to compute this rotation? This is our maybe let's say this is this one. This is this is from world coordinate to Manhattan coordinate. This is this rotation to align world coordinate and Manhattan coordinate. And then
but how does the camera play here?
Yes, after obtain this one, we need to compute rotation relation between camera and the Manhattan world, right? And since we have computer since the first rotation, it means RC0 and M. It already computed, right? We need to, if we want to...
Just to make sure, the first rotation is Manhattan to world. That's the first rotation computed?
Yeah, since the world is same to the world coordinate is first camera's coordinate, right? They are the same. So
the camera coordinate is the world coordinate, they're the same? It's a tautology?
Yes, only the first frame. Yeah.
Mm-hmm.
So this RMW means RM ceiling, C0, right? They are the same. So after obtain RC0M, then we need to update it to RCKM. How to do
Yeah.
that? Yeah.
Okay.
In this, yeah, let's go back. Yeah, maybe this. Oh, yeah, maybe this one. Yeah, let's see this G figure. Yeah. For example, if you find the first coordinate, first relationship between RC0 and
Yes.
Manhattan world, then
Mm-hmm.
you will then you can use this rotation to update RC1 Manhattan world. Yeah. So this is update and yeah, iteratively. Yeah.
The notation CNW is basically CN of Manhattan world. That's what the notation means. RCNW.
RCNW means from a word coordinate to camera coordinate. Yeah, this is a word to camera. RCM means from Manhattan to camera. Yeah.
Okay.
Yeah.
Okay. So we're saying we can estimate RCM because we have RCM -1.
Yeah.
The previous frame, right? That's why we can
Yes.
estimate the next one.
Yeah.
Okay.
Yeah. Then it means you have yeah, we can use this RCM -1 and M as an initial rotation, and then put it yeah, based on this initial rotation, we can project this it means RCM RCM frame, this RCM frame to the Gaussian sphere, and then use iterative process to generate RCK and M. It means we can from RCK -1 M, then after iteratively update process, we can obtain RCKM. Yeah, this is the process is mean shift process. Yeah.
So we have RCN, CM. We have it because it's the regular model from before Manhattan world. Then we have the RCM estimated because we can estimate previous RC big M.
Yes.
And now, so basically, but that's drifting by the definition. And how can we avoid drifting then?
Yeah, and we can use and since since in this process we will not use. I mean, yeah, we make use this initial pose as a kind of initial as a kind of initialization pose, but we will not. But in the iterative. But in the iteration, we will we will use current frames normal vector to obtain a new result. It means, in fact, so technically we will not rely on frames between them. I mean, yeah, you in fact you use RCKM in this process, but it can be removed in this process.
Okay.
In fact, yeah, this
How?
is yeah. For example, we make we input a value, but we let's say we input CKM, right, to obtain this CK plus 1M.
Yeah.
But our result didn't rely on this CKM. And why we can say that it yeah, in fact you can give a very bad in a very bad rotation as an interaction as a rotation pose. But if you give a good one, you can, the iteration will be converged fastly. But you also can give this CK minus 1M, not
Okay.
CKM. Yeah. So this, if you give CKM, it will be better, but you don't need to give it. Yeah. So this is why I say we can remove CKM. Yeah. And we can use it, but we don't need to rely on it. Yeah.
Yeah.
And
I think that's what we're missing, understanding that why, but if it's not in the talk today, it's okay.
okay.
Can I have a little try here?
Yeah.
If I understand correctly, so the reason you need the previous frame is that in a Manhattan world, your biggest risk of losing your place is if you mistake a wall for a floor suddenly, and you have a 90-degree rotation in your assessment of the world. But if you use the previous frame, you don't lose that. You know which way is up still. So you jump one frame forward. Now you still know which way is up, but you can correct your new estimate of the world by locking onto the 90-degree assumptions. And that gives you now back an absolute estimate of your Manhattan world, which you can then apply to the world, the original world transform.
Yeah. Thanks, Yang. Yeah, that's a point. Yeah, if we use RKM, we will not. If you turn on the camera, it sharply. We can maybe avoid such cases. If we use CKM, but in the algorithm, we don't need those neighbors frame. Enabling frames. This is why we call it a drift-free rotation. And why we use RCKM as input to update RCK plus 1M. Yang give the answers. Very good answers.
Thank you.
I also introduced for different frames, it will have different Manhattan frame. So based on this kind of orientation, we can compute the rotation matrix. And then based on this planar mesh reconstruction, another maybe we made a small application, and this is the reconstruction from RGB-D data set, and based on these plans, maybe we can make it into different OBJ files. Then it's easy to maybe retexture those planar regions in maybe planar regions on iPad. This is a kind of application. And furthermore, in our pipeline, after since we decouple 60 rotation, 60 pose estimation into rotation and translation. So after obtain some rotation, after obtain rotation matrix, we will only compute this 3D translation. What's the advantage of this step? It means in this step we don't need we don't need too many features, since compare the 3D optimization with the 6D optimization, we don't need too many features. It means we can maybe this method can suit some low textured areas in translation. This is another advantage of this idea. We have discussed some parallel and perpendicular features for planes and lines, but we also can use some relationships across features. For example, if some points, yeah, maybe it's left figure, if some points and lines are laying on this same plane, we can use this plane to represent those landmarks. So this is another function of coplanar features. Yeah, and you can see this is we introduced yeah, parallel or perpendicular features. It yeah, it exists in the same features, the same type of features, but for this kind of relationship, it can be found in some coplanar regions, yeah, and across points and lines, yeah. And how to use this stuff to improve our SLAM system? Yeah, here is yeah, another paper. Yeah, the input, yeah, it can be stereo views or just monocular plus IMU. After existing points and lines, and also maybe plain instance segmentation from networks, we can yeah, have some potential coplanar features, since we cannot trust these planar regions directly, so it's only potential coplanar regions. And then we yeah, if we sort the maybe in a planar regions, and then we will use a kind of ransack based on those 3D features to check whether this is a real plane or not. Yeah, after checking and removing some after layers, we will build another optimization based on coplanar parametrization. So this is yeah, my idea of this is finding some coplanar regions and try to use planar parameters to represent those landmarks, those coplanar landmarks. Yeah, this is inside of this paper. And yeah, yeah, this is details of this coplanar parametrization. In figure A, yeah, this is URAC data set. Yeah, it's also very popular for maybe VIO, yeah, and stereo or even monocular yeah, approaches. And the figure B is the result from our plane instance segmentation network. And yeah, and based on this, we can obtain some, let's say, initial planar regions, initial coplanar features. Yeah, and yeah, what's the advantage of this idea? And for traditional method, this is a Hessian matrix. Yeah, when we do some optimization, some nonlinear square optimization, and steps, we will use this Hessian matrix. For traditional method, yeah, this is the number of cameras. It means maybe 11 cameras in this stage, and maybe 27, and maybe 227 points and lines, and 2 planes in this traditional optimization model. If we can find some coplanar regions, it means we can use some plane, we can use those 2 planes to represent some features. Then the size of this Hessian matrix will be decreased. So yeah, you can save some powers and computation, yeah, based on these coplanar regions. Yeah, and for the details, maybe yes, as you know, yeah, we have some very popular parameterization for points like inverse steps. If you yeah, if you put this is n pi t and d pi, and they come from the parameter of plane of a plane. So if you merge this plane and inverse steps together, then you can find for this parameter, maybe we can call it depth or inverse steps, right? Yeah, and then you can find we can use left parts to represent it. Yeah, so yeah, it's very simple. Yeah, just in this way, we can use this plane to represent to take place of inverse steps. Yeah, and similar cases in this in those line functions. Yeah. Yeah, for line functions, yeah, we can use this parameter. Yeah, you can see from the original center of the camera and also endpoints of the line. And yeah, for this plane, for this blue plane, we have a normals, and also we have place normals. So we can use those two normals to compute the direction normal of this plane. So yeah, this is a way to represent normals, represent lines based on parameters of the plane, and also 2D and also 2D information of the line. So we will not. Yeah, we can build a similar parameterization for lines. Yeah, it's very similar to this inverse steps. So yeah, yeah, based on this idea, yeah, as we discussed, yeah, the size can be yeah decreased. Yeah, but here I didn't mean this method is better than this maybe this bigger Gaussian sphere. But in our paper, we tried even the size is decreased, but the performance of the system is not worse than original one. It means we just need yeah, maybe a smaller computation to achieve similar performance of other methods, yeah, other VIO methods or stereo SLAM or view approaches. Yeah, yeah, and then yeah, maybe we can have a quick yeah quick check in this nonlinear square optimization process. As we mentioned, we have some yeah, and as you know, we most of the time we would like to use maybe Gaussian maybe method and not yeah, we can use some Jacobian matrix maybe to represent this Gaussian matrix, and then for LM method, we will plus a structure of mu identity matrix. But sometimes the insight of this nonlinear square optimization method is we remove some parts of it. Let's say, yeah, for yeah, in those functions, it's easier to see that. Yeah, for example, this is our yeah, target function. Yeah, for R, it comes from error functions, right? It can be maybe we can make it as a reprojection error, and then we can build the target function. Yeah, and we after make it into linear function, we will have this optimization step. you can see for Gauss-Newton solver, it only use this step, Jacobian transform and Jacobian. But for LM method, it make this part into a mu and identity matrix. So it means both of them, I try to ignore this part or just use another part to replace of this part. So maybe if we can use another way, another lighter way to represent this part, that we can make the converge process smoothly and fastly. So based on this, this is the insight of different solvers in optimization stage. And in this part, you can see some reprojection errors. It's very common, right? You can build an error function. This is for this part. You can make the to this R. And then you will obtain. You can transfer it to lines and planes. For reprojection errors. Here. This is the some common method to compute maybe some boundary adjustment, right? Maybe I just want to show this process why some or maybe we can say when we can use this Gaussian-Newton solver and when we use this LM solver. If the input features and the initial pulse are very accurate, maybe you can use this Gauss-Newton. But if they are not very good and even very noisy, then maybe you cannot use it since it cannot converge finally. Since if you remove it means how width of this part compare with this Jacobian transfer Jacobian. If we for some good inputs, this part is very it can take a very important role. But for some bad inputs, this part will cannot be even removed directly. Okay. After that, maybe we can check some some easy topics. First of all, based on our traditional SLAM system like this Manhattan SLAM, we can try to add some try to generate some semantic maps. For our planar SLAM or Manhattan map, it's easier to obtain dense reconstruction map, but it both of them don't have some semantic information. So based on this semantic networks, we also can merge it into our SLAM systems. And after some filter, we also can build you can see at the bottom, we also can build a semantic sparse map. You can see this is a TV and the rest you also can find that. And based on that, we can generate a consistent object mask. And when in this paper, we feed masks, 2D masks, and our dense 3D reconstruction into the network together. And here we can obtain a semantic dense segmentation result. This is a kind of usage for semantic networks in SLAM systems. And here you can see some results, results compared with state-of-the-art networks. And benefiting of those 2D masks and maybe in some small regions, and in some small regions, our method can do better than this 3D segmentation network. Yeah, yeah. This is you can see some prediction labels at the bottom of the figure. And finally, I would like also introduce some maybe related papers in this area. Maybe in this CubeSLAM is also very popular. If you can find some, if you can find 3D bounding boxes for objects, you also can build the traditional graph into static point and a dynamic point. It means maybe points lying some objects can be dynamic. So maybe you can take some different strategies to deal with static point and dynamic point. So if you use it in some dynamic scenarios, maybe it will be more robust. Since for traditional method, we regard every features equally, so it's not very smart. So maybe this method also propose a kind of proposal to solve some dynamical scenarios. Both of them, this one and this one, try to use semantic stuffs into SLAM systems to achieve better performances in reconstruction or in post-estimation. There are really lots of topics in this area. A lot of open topics. This is my talk. Thanks. Thanks.
Okay, we still have 15 minutes on the schedule. If anybody here has questions, it's the time.
We have discussed Manhattan. Maybe if you have questions, about other sections or suggestions, we can discuss them.
You didn't mention, I don't think, anywhere during the Manhattan World assessment whether you can determine verticality from the features, or do you have to retain an IMU to be sure of the vertical in your world?
Okay, but in our Manhattan SLAMs, Manhattan systems, we didn't use IMU. We just use monocular and RGB-D sensors.
Okay. So there's no real world up in those reconstructions. There's really there's just tracking.
But for the mapping part, it's not very good. But we have you can see that this is our Manhattan world's mapping result. It's not real dense mapping, but you can see point lines, planar regions, and also this dense planar mesh reconstruction. Not the really fully dense reconstruction.
Thank you.
Thank you. This system is open source. If you are interested in it, you can check it.
Okay, I don't think I have questions. I don't see. Let's see on the YouTube. Make sure. I don't think I saw, but while estimating the normal map, you have used the spatial. Oh, we have one.
Mhm.
On slide 15 from YouTube from Nile. While estimating the normal map, have you used any special regularization for getting better coverage? Special regularization?
Maybe no. We just use some very common layers. And we use ResNet. We tried ResNet 50 and ResNet 101 as our backbone, and try to add a clustering. Yeah, and here we are very similar to this mean shift clustering, and try to use a clustering method to maybe push and pull those deep embeddings to make sure maybe similar normals can, maybe the direction of those similar normals can be close than ever before. This is we used. Just some very common layers, collagenal layers. Yeah.
Okay, let's wait for a response. So yeah, I think we will wrap it up. Yanyan, if you have anything to close off with, that's the time. Otherwise, I'll close the event.
Okay. Yeah. Thanks. Yeah.
Okay. So thanks everybody who stayed all the way through. Very technical talk today we had. Thank you, Yanyan, for taking this time and giving us of your knowledge. Maybe it's a good time also for me to post again all the places where you can find us: the subreddit, the newsletter, the YouTube where this will be recorded and posted, the Discord server for the instant messaging. I will say thanks for everybody in the community, those who joined today and those who are taking parts at other times. This is such a fun thing for me to organize and do with everyone around the world. And with this, I will say bye to all. Good night, good morning, good day, wherever you are.
Yeah, Peter. Thanks for organization. Yeah, thanks.